So in the last class, I proved Kraft's inequality and the Kraft-Macmillan's inequality. Right? So Kraft's inequality says that any prefix-free code, given any prefix-free code with code word lengths, say L of x, the Kraft sum, which is summation over all x, 2 to the minus L of x, this should be less than or equal to 1. So this gives a necessary condition on the code word lengths for any prefix-free code. Right? And there's also a converse which says that for any set of code word lengths that satisfies Kraft's inequality, there exists a prefix-free code. The same thing also holds for uniquely decodable codes. So for any uniquely decodable codes, the Kraft sum must always be less than or equal to 1. And by the converse, for prefix-free codes, there also exists a uniquely decodable code as long as the code word lengths satisfy Kraft's inequality. Okay, so this gives us some conditions on the code word lengths of any prefix-free code or any uniquely decodable code. So among all possible prefix-free codes or uniquely decodable codes, what is the minimum expected length? That's the question we want to answer. Right, so this is the question we want to answer. Is it true that we can still get close to entropy? Is there any loss in assuming that the code has to be uniquely decodable? All right. So this can be reformulated in the following way. We know that any uniquely decodable code must satisfy Kraft's inequality. Right, so the code word lengths must satisfy Kraft's inequality, and if the code word lengths satisfy Kraft's inequality, then there exists a prefix-free code and therefore a uniquely decodable code. So this is the same as saying for a given distribution Px, what is the minimum over the code word lengths L1 to, suppose that there are m symbols in the alphabet. Among all code word lengths that satisfy Kraft's inequality, what is the expected length? Size. Is this okay? Is this objective clear? So we're given a distribution Px, right, a probability mass function on m symbols. If I give you a sequence of code word lengths, the expected length of the code is exactly summation I going from 1 to m, Pili. And since we want the code to be uniquely decodable, we want the lengths to satisfy Kraft's inequality. So this should be less than or equal to 1. All right. So finding the minimum expected length among all possible uniquely decodable codes essentially boils down to finding a set of lengths that satisfy Kraft's inequality and minimizes this summation Pili. So this is a well-defined optimization problem and one can just try to solve it somehow, maybe numerically. Note that this is a combinatorial optimization problem because we want the lengths to be integers. They have to be positive integers. It's not a continuous variable optimization problem. All right, that's something to be kept in mind. So for large M, it may not be so easy to solve in general. But then we'll see a different way as to how this optimization problem can be solved efficiently. So even before solving this optimization problem, we could try to at least get bounds on what is the minimum expected length. All right. There's one approach. One approach is to find a relaxation of this optimization problem. That is, you ignore the integer constraint and you solve the continuous variable optimization problem. If you do that, then the minimum can only be lower. It can't be any more than what this is, because you are minimizing over a larger space of continuous variables, not restricting yourself only to integers. And then you can try to solve that optimization problem, and that will give you a lower bound. All right? That's one way of going about it. But we'll see a more information theoretic proof, which is simpler. You don't have to go through a lot of calculations. All right? So in fact, let us call this quantity L star of Px. All right. One thing to note is that this optimization problem is the same irrespective of whether you are looking for uniquely decodable codes or prefix-free codes, because both codes have to satisfy Kraft's inequality. So really there is no loss of generality in restricting yourself only to prefix-free codes. Because if you look at the larger class of uniquely decodable codes, you end up with the same optimization problem, and therefore the minimum expected length is still the same. You can't lower the expected length even if you take the more general class of uniquely decodable codes. There could be other codes, non-prefix free but uniquely decodable codes that achieve the same minimum. But there will always be a prefix free code that achieves the best expected length as that of a uniquely decodable code. So we'll show that the minimum expected length for prefix-free codes or uniquely decodable codes is lower bounded by the entropy of Px, and it is upper bounded by the entropy of Px plus 1 bit. All right. Now compare that with the best code if we didn't have any prefix-free or unique decodability constraints. In that case, we had an upper bound on the minimum expected length equal to the entropy, and there was a lower bound which is entropy minus log of E times the entropy plus 1. All right. So there is some loss in assuming that in restricting yourself to unique decodable or prefix-free codes. But that loss is not too much. That's the point here. Okay, so let's prove the upper bound first and then go to the lower bound. So to prove the upper bound, it's good enough to show the existence of one code that achieves one prefix-free code that achieves a rate or expected length which is at most h of x plus 1. Okay. And if I want to show the existence of a code, we already have one technique at our disposal. You find a set of code word lengths that satisfies Kraft's inequality. So given a Px, if I can find an explicit set of code word lengths that satisfies Kraft's inequality, then it means I can also construct a prefix-free code with those lengths. So we'll do the following. Given any x, I'll define L of x to be equal to the ceil of log 1 over P of x. So this will be my set of code word lengths. It's effectively log 1 over p of x, but with the seal, because I want it to be an integer. All right. Now, does this satisfy Kraft's inequality? Does this set of code word lengths satisfy Kraft's inequality? Let's look. So you take the summation over all possible x, 2 to the power minus L of x. This is the Kraft sum. This is sum over all possible x, 2 to the power minus seal of log 1 over p of x, which is at most, now seal log 1 over p of x is greater than or equal to log 1 over p of x. Right? So negative of seal of log 1 over p of x is less than or equal to negative of log 1 over p of x. So 2 to the power negative of seal of log 1 over p of x is less than or equal to 2 to the negative log 1 over p of x. Which is sum over all x, 2 to the log p of x. But what is 2 to the log p of x? This is p of x. And this sum is equal to 1. So this choice of code word lengths, L of x equal to seal of log 1 over p of x, this satisfies Kraft's inequality. Right? So there exists uniquely decodable and exists a prefix-free code that which with these code word lengths. Right? Any questions? Okay, so there exists a prefix-free code. What is the expected length of this particular prefix-free code? The expected length is sum over all possible x, p of x times L of x, which is seal of log 1 over p of x. Right? What can you say about seal of log 1 over p of x? It's less than or equal to log 1 over p of x plus 1. The first term is just the entropy and the second term is 1. So now we have given an explicit prefix-free code or a way to construct a prefix-free code with expected length at most h of x plus 1. So there's one code that achieves expected length at most h of x plus 1. So the minimum possible expected length can only be less than this. So L star of Px is at most h of x plus 1. Doesn't matter, right? So there could be codes that are worse than this. There will definitely be codes that are worse than this. But the best code will only be better than this. All this says is the minimum expected length for the best code is at most this quantity.
But you only showed existence for none case.
Correct. So there is some code that achieves a rate which is, or expected length which is h of x plus 1, right? So if you take the minimum over all possible codes, that can only be smaller. Because this is the expected length of the best possible code. If there is one code that achieves this expected length, then the best possible code will achieve an expected length that is less than this, potentially.
It's only less, it's strictly less than.
Which one?
Ceiling is strictly less than.
Not really, right? If log 1 over p of x is an integer, I'm sorry, I didn't quite get it.
It's not less than equal to.
Okay, fine. I agree. It's strictly less than this. Yeah. So this is a strictly less than. But you can get pretty close to this. Now let's prove the lower bound. For the lower bound, again, we'll only use properties of these information measures. So let's start. I'll define. We're given a probability mass function p of x. I'll define the probability mass function. Let me do this. Let's start with the optimal code. For the given distribution Px. Okay, so this is the code that achieves the minimum. This is that prefix-free code that achieves the minimum expected length. So basically, it is that prefix-free code for which the expected length is equal to L star of Px. And let L star of x be the code word length assigned by this particular code for the symbol x. Okay. Using this set of code word lengths, I'll define the probability mass function qx of x, which is 2 to the power minus L star of x, which is normalized, so divided by sum over all x prime, 2 to the power minus L star of x prime. Right? So this is a valid probability mass function. Okay. Let's look at the KL divergence between Px and Qx. We know that the KL divergence is non-negative, and this is equal to summation over all possible x, P of x, log P of x by Q of x, which is P of x divided by two to the power minus L star of x times summation over all x prime 2 to the power minus L star of x prime. Okay. What is this particular quantity?
minus L.
It's the negative of the entropy. So let's take that out. So I have the negative of the entropy plus I'll isolate this particular quantity. So log of 1 over 2 to the minus L star of x is log of 2 to the L star of x, which is just L star of x. Plus sum over all x. All that remains is this particular quantity, P of x log sum over all x prime 2 to the minus L star of x prime. So on the right hand side I have negative of the entropy plus what is sum over all x P of x L star of x? That's basically the minimum expected length. L star of Px plus this particular quantity, this outer summation is over x, and the inner summation is over x prime, which is a different variable. So the outer summation just sums to 1. So I have log sum over x prime 2 to the minus L star of x prime. Correct? But the code word length, so this is a prefix free code, right? Or at least a uniquely decodable code. So this should satisfy Kraft's inequality. Huh. The last term. So this summation is over x. Correct? So this term inside the log is just a constant in terms of x. Right? So this quantity is less than or equal to 1 by Kraft's inequality, or the Kraft-Macmillan. Right? So since it's log of something which is less than or equal to 1, that quantity is less than or equal to 0. So the minimum expected length is at least the entropy.
So we wrote an expression for the ceiling value above for proving the upper bound.
Correct.
There we could have just written that the ceil value is greater than equal to the actual log value, and then it could have.
But that is one code, right? I don't claim that that is the optimal code. So in the first part of the proof, I used one particular set of code word lengths. But this set of code word lengths may not be optimal. This may not give you the minimum expected length. But based on our proofs, what we see is that it is not too far away from the minimum expected length. It's only within 1 bit from the minimum expected length. Any questions? Okay, so now that we have some bounds, we also have an explicit algorithm to get a prefix-free code that achieves something close to this particular bound. But then the gap that can be achieved can potentially be large. Right now we see that it's just 1 bit away from the entropy. But remember what we were trying to do? We were trying to design a symbol-wise source coding scheme. So you're given a sequence of length n. You're given a sequence of length n, which you encode. You encode this to get encoding of x1 concatenated with the encoding of x2 and so on, xn. Where this encoding is essentially a prefix-free code or a uniquely decodable code. So we know that the expected length for each symbol is going to be between h of x and h of x plus 1. Correct? So what can we say about the expected length of the best possible encoding of xn? What will the expected length be? It will just be n times the expected length of each symbol, of the encoding of each symbol. So this is going to be at least n times the entropy of x, and at most n times the entropy of x plus n bits. All right. So earlier when we looked at the optimal source code, right? So if you took the block of n symbols at a time, constructed the optimal source code, we know that at least for a memoryless source, the expected length L star of xn, this is without So if we didn't have those unique decodability constraints, if we were willing to sacrifice computational efficiency, then we could achieve an expected length which is at most n times the entropy, n times h of x, right? This is what we saw in the very beginning of the course. But now with these unique decodability constraints, we see that it can be anywhere between n times h of x and n times h of x plus n. So if we have a large block and we encode one symbol at a time, then potentially we may have to pay an extra penalty of n bits, which can be large if n is large. So you want to definitely do better. The advantage of this particular approach is that the computational complexity is only linear in n. So is there a way of still getting roughly the same computational complexity but do something better than n times h of x plus n? That's what we will be trying to do. But even before that, now we have one particular scheme that gets us an expected length that satisfies these conditions, right? You just take the length to be log of C of log of 1 over P of x, and that is going to give you one particular scheme. But as I said earlier, it's not the best possible scheme. So let's say that it is within, suppose that the scheme that we had. So this is what I call the Shannon code, wherein you take L of x to be equal to which one? It's linear in n, right? Assuming a fixed input alphabet. Because you're encoding symbol wise. Correct, but then when I said that's a complexity, the complexity is only as a function of n, not as a function of the size of the alphabet. So this is one particular code. You take this to be the set of this to be the length, and you construct the binary tree and use the converse part of Kraft's inequality to get a prefix-free code. So let me call L Shannon to be the expected length of this particular Shannon code. Okay. And let me say that the length of the Shannon code, expected length of the Shannon code, is slightly larger than the minimum possible expected length by 0.01 bits. All right. This may not seem like a lot. All right. But then if I want to encode n symbols now, then I have n and n over here. So I have to now pay a penalty of 0.01 times n. So if n is large, this can make a big difference. And I want to save as much as possible. So now is there a way of constructing the best possible code? What is the best possible code? Which one? Because we haven't shown that it is optimal, right? There could potentially be something better than the Shannon code. In fact, let's look at perhaps a simple example. Let's say this is 0.9 or I don't even have to go that far. Suppose I just have two symbols, all right, 0 and 1. And I want to use Shannon for whatever reason. It's a dumb example, but I still want to use Shannon code. What would be the lengths given by Shannon code? What is log of 1 by 0.49? Yeah? Correct. So 1 by 0.49 is something that is slightly more than 2, right? So log of something slightly more than 2 is something that is a little over 1, and the seal of that is going to be equal to 2. So the Shannon code is going to give me one code word which has length 1 and another code word of length 2, which is clearly suboptimal. Right? And in this case, what is the expected length going to be? Yeah? It's going to be 2 into 0.49 plus 1 into 0.51, which is just going to be 1.49. But what is the minimum expected length in this case, in this toy example? 1, right? So it's away from the minimum expected length by 0.49 bits. It's not even a small quantity. Right? So the Shannon code can be very suboptimal, because even in this kind of trivial example, the Shannon code does badly. And it can do even worse, right? Because let's say that px of 0 is 0.0001 and px of 1 is 0.999. Again, the optimal code is just 1, but the Shannon code is going to give an extremely long code word for the first symbol.
What if we start with the highest symbol,
Okay.
the symbol of the highest probability,
Okay.
and for the last symbol we just satisfy that. Here you've used 2 power minus 1, this is half, so the rest of it is half, so you want to use 1 by 0.
But again, this is sort of a trivial example, right? There could be much more complicated examples where you have many symbols. The alphabet could be fairly large, and even then the Shannon code assigns suboptimal code word lengths. Right? That will happen. But instead, we'll come up with a solution that's optimal anyway. All right?
Can we say that a code doesn't satisfy Kraft's inequality
That doesn't satisfy Kraft's inequality with equality.
Equality if it's strictly less than 1, it is
We'll see. Okay. So based on this particular example that we had over here, we'll try to construct an optimal code. So there's a backstory behind Huffman codes. So apparently Huffman this was invented by David Huffman, I think back in 1951 or so. He was a PhD student, and he was attending a course with Robert Fano, who was a faculty member at MIT. So in his course, Fano said, you can either take your final exam or you can do a term paper. I'm going to give you a problem, sort of like a take-home exam in some sense. And Huffman didn't want to take the final exam, so he said, okay, I'll do the term paper. And the term paper was construct an optimal prefix-free code. All right. Now, what Huffman didn't know that this was an open problem. And Fano just gave this problem without, I'm assuming, without really expecting him to solve this problem. And Huffman didn't know that this was an unsolved problem. With some difficulty at the very end, he was able to solve it. And he came up with this particular code. And then published a paper, right, which became the Huffman code. But then later, apparently, Huffman said that, okay, if I didn't know that this was if I actually knew that this was an unsolved problem, then maybe I would have not got the solution. It is because I thought, okay, this is just a term paper, I'll be able to solve it. Right? So sometimes the perceived difficulty makes it harder to get a solution rather than the actual difficulty itself. And again, the Huffman code, as you will see, it's a pretty simple algorithm, but what takes a little bit of effort is to show that this is optimal. And it's based on just a very simple algorithm. What you do is, let's consider the code tree. All right, of some prefix-free code. Let's say that this should be an optimal prefix-free code. And so I have 4 symbols, and maybe this is the code word tree of the optimal, or this is the optimal code word tree for a prefix-free code on 4 symbols. What can you say about the probabilities of these 4 symbols? Just a guess. So I have A, B, C, and D. So one natural thing to expect is that the probability of A should be greater than the probability of B. Can it be equal to the probability of B? Can all of them have equal probability and still get this code word tree? Yeah, somebody. The question is, so firstly, it's natural to expect that the probability of A should, suppose that this is the optimal code for some PMF on A, B, C, D. All right. What all can we say about the probabilities of A, B, C, and D? It should be the case that probability of A is greater than or equal to probability of B, which is greater than or equal to probability of C, greater than or equal to probability of D. Okay. But the question is, can this be the optimal code tree if probability of A equal to probability of B equal to probability of C equal to probability of D? Suppose all of them have probability 1/4 each. Can this code tree be optimal? How many say yes? This can potentially be optimal. How many say no? It's okay, take a guess. Right? Okay, why do you think it's not the case? What does your gut tell you? Okay, in this explicit case, when all of the probabilities are equal, you can find the expected code word length. What would that be? So the expected code word length would be basically 1 plus 2 plus 3 plus 3 by 4, right? So this would be the expected code word length corresponding to this code if all the probabilities were equal. But then here is a simpler what would be the code word length for this code, the expected length for this particular code, assuming all the probabilities are equal. So this would give me an expected length of 2, which is less than 9 by 4.
If the number of symbols were 3,
If the number of symbols were 3, um,
then like we could have two different cases which still get the same expected length.
that's okay. I'm just talking about this specific thing. I'm just trying to develop intuition over here. All right, nothing else. If there were 3 symbols, then basically A and B would be just this here, right? So 3 symbols. That would give the expected length.
No, but like even the same thing is same to the same.
What do you mean the same?
Like if you're about D in this.
So then C would have a code word length of 3, right? Which is not good. All right. So Huffman's solution was basically the following. You start with the 4 symbols. All right. And let's try to come up with a very greedy procedure. We know that if there are only 2 symbols, what is the optimal code? You assign 0 to one symbol and 1 to the other symbol. Right? So if there are 2 symbols. Suppose there are 3 symbols, A, B, and C. What would be the optimal code? So the optimal prefix free code would be you assign 0 to one symbol, 1 0 to one symbol, and 1 1 to the third symbol. Why is this optimal? It satisfies Kraft's inequality, but how do you know that you can't do any better?
Because if you put 1 instead of 1 0, it will be
So basically, if for it to be prefix free, clearly at least one symbol has to have code word length of 2, right? Can there be 2 symbols of code word length 1? You can't, right? So 2 symbols have to have code word length 2. There can be at most 1 symbol with code word length 1. So this is the minimal set of symbols that you can do. All right. Okay, so now there are 3 symbols. Which symbol would get the code word 0 and which symbols would get 1 0 and 1 1? So the one with the largest probability would get the code word 0 0, and the other 2 would be 1 0 and 1 1. For now, let's assume that A has the highest probability and B and C have probabilities that are less than or equal to that of A. All right. We know that in the 2 symbol case, the optimal code word or the optimal set of code lengths are 0 and 1. In this case, what we try to do is let's try to reduce the 3 symbol case to the 2 symbol case. So what we can do is we can merge B and C to form a super symbol. Let's call this BC. And B is assigned 0 and C is assigned 1. So now I have 2 symbols, A and BC. And the probability of A is the same as before, but the probability of the super symbol BC is the sum of the probabilities of B and C. Okay. So now I've successfully reduced it to the 2 symbol case, for which this is optimal. Okay. So more generally, let's say I have any number of symbols. We do the following. We'll sequentially merge symbols with the least probabilities to form super symbols. So now you go from alphabet size m to alphabet size m minus 1. And then you keep repeating the same thing over the super symbols. So maybe in the first step, I merged D and E because they had the least probabilities. But perhaps at the next stage, the probability of D plus the probability of E could potentially be larger than maybe probability of B and probability of C. So maybe in the next step, I'll have to merge B and C. So at the end of the first step, I end up with 4 super symbols, A, B, C, and DE. So in the second step, I merge B and C to get a super symbol BC. So at the end of the second step, I have 3 super symbols, A, BC, and DE. Now again, depending on the probabilities of the super symbols BC, DE, and A, you may have to merge certain other symbols. Maybe you have to merge these two, and so on. All right. So let's maybe see a concrete example. Suppose I have the following probabilities. I have A, B, C, D. Say this is 0.2, 0.25, 0.3, 0.2, 0.2, 0.2. Okay, so I have 5 symbols with these probabilities. Now the first stage of the Huffman coding procedure is you merge the 2 symbols of the least probability. In this case, the symbols are D and E. So I'll merge D and E to get a super symbol. Let's call it DE. And this has probability 0.3. The rest of them are left as it is. Now next step is, again, you merge symbols of the 2 symbols of the least probability. Which are those 2 symbols? B and C, right? I have 4 super symbols now, B, A, B, C, and DE. Now in this case, the probabilities are 0.3, 0.2, 0.2, and 0.3. So I merge those 2 symbols which have the least probability, which is 0.2 and 0.2. So I merge B and C. So this is 0.4. Alright, and the next stage, so when I merge 2 symbols, I assign them code word bits, say 0 and 1, 0 and 1. If I don't merge symbols, I don't assign them anything. Alright, so what's next? Which ones should I merge? I should merge A and DE because both of them have probabilities 0.3 and 0.3. .6 and give them bits 0 and 1. And I have only two symbols left now, so I'll merge these two to end up with just one super symbol, A, B, C, D, E. Alright. So now I get a tree which seems a bit complicated to look at, but how do you get the code word for a particular symbol? So this would essentially correspond to the root, and you traverse from the root to the particular node. So if I want the code word for A, that would be 0, 0, and that's it. If I want the code word for B, then this would be 1, 0, and that's it. The code word for C would be 1, 1. The code word for D would be 0. I'm sorry. Yeah, it would be 0, 1, 0. And that for E would be 0, 1, and 1. So if I had to rewrite this tree, I have the root which has probability 1. I have 0 and 1. So 0, 0 is A. And 0, 0, 1, 0 is D. And 0, 1, 1 is E. 1, 0 is B. And 1, 1 is C. Right, so this would be the code tree for this particular code. Questions? So for this particular code, what is the craft sum? It's equal to 1, right? I'm sorry? We'll see why this is optimal. I don't claim, right now we haven't shown that this is optimal, but this is some procedure. This is an algorithm that gives us a prefix-free code. It may or may not be the best. All right, but since we are almost out of time, we'll stop here. But in the next class, we'll show that this procedure gives us an optimal code, that you can't do any better than this.